Hello and welcome. Today we're going to dive into one of the most fundamental, most versatile, and honestly most essential components in all of modern electronics. Seriously, if you've ever listened to music, used a medical device, or really interacted with any piece of tech, you've definitely benefited from its power.
So, what is this mystery component, right? This single building block that's at the heart of countless circuits, from the super simple to the mind-bogglingly complex.
You got it. It's the Operational Amplifier, or Op-Amp for short. This little integrated circuit is a true workhorse, kind of like a Swiss Army knife for anyone designing analog circuits. Okay, let's get into it and see what makes this thing so special.
So at its core, the whole concept is incredibly simple. Just think of it like a black box, right? It's got two inputs, a plus and a minus, and just one output. The op-amp's only job, its entire reason for being, is to look at the tiny voltage difference between those two inputs and amplify it by a massive amount. It literally takes a whisper and turns it into a roar. And when I say massive, I mean it. A classic op-amp like the 741 has what we call an open-loop gain of around 200,000. That means a 1 microvolt difference at the input could, in theory, create a 200 millivolt output. Now that raw power is incredible, but on its own, it's also really unstable and pretty much impossible to control. So, how do we tame this beast? Well, the secret, and this is the key to almost everything the op-amp does, is this beautifully elegant concept called negative feedback. By taking a small piece of the output signal and feeding it back into that negative input, we create this self-correcting loop. It's kind of like cruise control in your car, you know? It's constantly checking the output to adjust the input, which makes the whole thing stable, predictable, and incredibly useful. This whole feedback idea is so powerful that it lets engineers simplify the really complex reality of the op-amp down to a wonderfully simple, ideal model. This is how we can actually design with it without getting totally lost in the weeds.
And that ideal model? It boils down to just two golden rules. First, the inputs have infinite impedance, which is just a fancy way of saying they're perfect listeners. They sense the voltage, but they don't draw any current. They just look, they don't touch. And second, thanks to that high-gain feedback loop, the op-amp will do whatever it has to at its output to make the voltage at the two inputs exactly equal. Remember those two rules and you can analyze pretty much any op-amp circuit. It's really that straightforward.
Okay, with those rules in our back pocket, let's see how they play out in the two most basic setups. Just by using a couple of resistors, we can make the op-amp behave in two main ways: inverting and non-inverting. See, the arrangement of these external resistors is everything. They're what forms the network around the op-amp that sets the gain, the input impedance, you name it, the whole behavior of the circuit. It's how we take all that raw, untamed power and shape it into a precise, predictable tool for a very specific job. So it's all about choosing the right tool for the job. With the inverting setup, the output is a mirror image of the input. It's flipped 180 degrees. Because of how it's wired, the input is held at a steady 0 volts, what we call a virtual ground, which is perfect for things like audio mixers where you want to add a bunch of signals together without them messing with each other. Now, on the other hand, the non-inverting setup keeps the output in phase with the input, and it has an incredibly high input impedance. That means it doesn't disturb the signal it's trying to measure. This makes it an absolutely perfect buffer, like a bodyguard for a sensitive signal, letting you measure it without drawing any current at all.
And this just brilliantly illustrates why op-amps totally revolutionized electronics. As the author Sergio Franco points out, negative feedback turns the hard problem of gain into a simple matter of just picking a resistor ratio. Need a gain of 10? Simple. Just make one resistor 9 times bigger than the other. It makes designing circuits so much more intuitive and stable. It's genius, really.
This predictability and this versatility, that is exactly why you find op-amps in practically every corner of the electronics world. Their applications, well, they're seemingly endless.
And I mean, they are everywhere. In the audio world, they boost those tiny signals from microphones, and they act as active filters to shape the sound you hear. For sensors, they take weak signals from things like temperature probes and make them strong enough for us to measure. They can even be set up to generate the exact waveforms that test equipment relies on, or to convert the faintest glimmer of light from a photodetector into a voltage you can actually use. Every single one of these is a fundamental building block on its own, and they're all made possible by the humble op-amp. Now, what's really cool is how even the op-amp's limitations can become features. See, an op-amp can't output a voltage that's higher than its own power supply. When it tries, the output just hits a wall. It saturates.
You can see it right there on the graph where the line suddenly goes flat at the top and bottom. But here's the thing. Instead of a bug, this is a feature. That super sharp transition from low to high means the op-amp is now acting like a high-speed switch, telling you instantly which of its two inputs has a higher voltage. This makes it a fantastic voltage comparator, a completely different tool, all built from the very same part.
So when you think about it, the op-amp took the incredibly complex problem of making a stable, high-gain amplifier and just packaged it. It put it into a simple, reliable, and cheap little building block that unleashed decades of innovation. And it kind of makes you wonder, right? What complex engineering challenge of today is going to be abstracted away into the simple black box of tomorrow for the next generation of designers to build with?